The next two sections are all about the properties of powers and exponents, which we've already kind of talked about before when we did the mid-chapter 6. So this is going to be a fairly quick lesson that I should be able to go through pretty quickly, and you should be familiar with most of the properties. But I figured it'd be good to review it anyway, and since it's in this chapter, why not? The question for today is, how do you simplify expressions that have powers? So we're just going to go through all the properties. Maybe one or two new ones. I don't think so. I think you're going to know all these. And a lot of these fill in the blanks are pretty much the same thing, so just kind of follow through and fill these in. So we're going to do the product of powers postulate, which says any non-negative base, so positive numbers, b, and as long as it's not a zero exponent, m and n, or any non-zero base b and integer exponents, m and n, then we have this property. So this is just, you just read through this. It's nothing special here, but these are the kind of restrictions on it. We have b to the m times b to the n, and as you know, between these two, what would you do? You would have to add exponents. So that would be b to the m plus n. So you just add the exponents. Let's do blue. So we'll try some examples with numbers. Simplify the following expressions and show your work of what operation you're doing. Okay, so what we're doing here is we're going to be adding them together. So we have 2 to the third times 2 to the fourth. You keep the 2. You do not multiply the 2's together, and you add the exponents, 2 to the seventh. Now, we could put 2 to the seventh in the calculator and keep going, but I just want to practice the property right now. Later, you'll be required to actually simplify it completely. All right, then 10's here. We just add these. You get 10 to the 12th. 7's here, put them together, you get 7 to the 9 plus 11 is 20. All right. Now down here, for example 2, we're going to solve this equation, trying to figure out what would you have to put in there for x. Now you might be able to look at this and just immediately figure it out. 3 plus some number gives you 10. But there's also ways to do this when it gets a little more complicated where you set up an equation. So you just go through the exponents, 3, x, and 10, and make an equation. What would you do to these two exponents to get 10? You would add them together. So really what we're saying is 3 plus x equals 10. So we'll write that out as an equation. I know, again, you might think it's kind of stupid right now because you're like, oh, I know what the answer is. It's obviously, 7, right? But I think it's better to just write this out as an equation and figure out how I'm getting this. I'm just adding the exponents together, equaling the other exponent. So what you would do with an equation like this is solve for x, which is very simple. You would minus 3 on both sides, and that's where you get your 7. So you can also solve these for the variables and in the exponent spot. All right, the next one, we're going to do division, quotient. A lot of stuff, again, is the same fill in the blank. For any positive base b and real exponents m and n, or any non-zero base b and integer exponents m and n, all this long stuff just to basically give you the property, b to the m over b to the n. What do we do here? We subtract exponents, b to the m minus n. So let's go through and subtract them. 10 to the 12th over 10 to the 4th. Subtracting exponents, you would get, right, we're subtracting by 4, 10 to the 8th. 12 to the 8th over 12 to the 3rd. You keep the base the same. Don't forget, the base stays the same here. Still b. 8 minus 3 is 5. And then 190, we're going to do 190. Subtract here, we get 18. Which again would be a very big number, and you can simplify all of these, but I'm not going to do that. I'm just practicing getting the exponents the right one. All right, and then the fourth example here, we're going to solve this. If we had something minus 6 equals 3, that's what we're looking at here. I'm going to make an equation out of that real quick. We have x minus 6 equals 3. We could solve this and add 6 to both sides. Again, you might be able to figure out what this is just by looking at it, but I'm going to show the work on how you would solve this algebraically. It would be 9. So 9 minus 6 is 3. I think they get a little bit more difficult than that, so I want to make sure you know how to do that. All right, the next property, which I think a lot of students might struggle with, this is called the power of a product postulate. So it's like a power to another power. For any non-negative bases a and b, and non-zero real exponents m, or any non-zero bases a and b, and integer exponent m, then we have this. So we have two things inside a set of parentheses with an exponent on the outside. So really it's kind of like distributive property where the m is going to go as an exponent to both a and b. So we would say this is a to the m times b to the m. For example, y to the 6th, we would do x to the 6th, and then y to the 6th. Just goes to both of them. Boom, boom. B, we would do 2 to the 3rd times x to the 3rd. Now, I am going to simplify this one because we've done this before, and it's not that big of a number. 2 to the 3rd is 2 times 2 times 2, which is 8x cubed. That's your answer. And the same thing for the last one. 5 goes to both of these, so we have 5 to the 4th, y to the 4th. It's not a great looking 4. Now, 5 to the 4th is 5 times 5 times 5 times 5. So that's like saying 25 times 25, which is 625. So just make sure that you're not doing 20 here, 5 times 4. You're not getting 20. It's not the same thing. Power to another power there. Okay, so we can do the same thing as if we have a fraction in there. No different, really. So for any non-negative bases, a and b, and real exponents, n, or any non-zero bases, a and b, and integer exponent, n, then we have this property here. All right, so what we can do here is the same thing that we did before. The n is going to go to the a, and the n is also going to go to the b. Although they used a different letter last time, didn't they? They used m. Okay. So we're going to say it's a to the n divided by b to the n. I'm not sure if we really went over this in depth, but I know we talked about it a little bit. All right, so we have x to the 7th power, and the 7 has to go to the y. So x to the 7th over y to the 7th. The next one, we're going to do 2 to the 4th. It goes to both of these. Over 3 to the 4th. Now I'll simplify this. 2 to the 4th is 2, 4, 8, 16. 3 to the 4th would be 81. There's your answer. All right, the 3 here goes to both the 3. So 3 to the 3rd, 7 to the 3rd. 3 cubed is 27. And then 7 cubed, I think, is 343. So I am actually simplifying them now, just going a little bit further, just to practice it a little bit. But the property that we're practicing is just taking a power on the outside and putting it into a fraction. All right, we have, I believe, 2, 3 more. Okay. And then I think we're done after that. Okay. So example 6. I'm going to solve this expression 2 different ways. So there is a possibility that you can actually, I'm going to show you that this equals the same thing. I mean, you can clearly see that 3 to the 7th over 3 to the 7th, we're starting with the same problem, but I'm going to show you how to solve it 2 different ways. Okay. So one way is to look at this and say, okay, they have the same base, right? I'm just going to subtract exponents. So it's going to be 3 to the 7 minus 7, right? Which would be 3 to the 0 power. Now the question is, what is 3 to the 0? Well, I'm going to leave it like that for now. I'm going to go over to this one. If we go back to this again and say, how else could we solve this? Well, one of the other ways you might think about solving this is if you saw just the number 3 over 3. One way you might do that is you would probably cross them off and say, oh, 3 divided by 3, okay, 3 goes into 3 one time. So the same thing could happen here. You have the exact same thing on top and bottom. They would cross off and it would become 1. Or you could say, 3 to the 7th goes into 3 to the 7th how many times? 1 time. So we have this thing where we solved it 2 different ways. We got kind of like similar answers here. But because we start with the same thing and got 2 different answers that look different, we can then say that this answer is got to be the same thing as this answer. So 3 to the 0 power is actually 1. Right? Does he follow that? We started with 2 problems which are exactly the same. I solved them 2 different ways. Hopefully you followed that. So therefore these have to be the same. So what does that tell us? If b is not 0, it can be any number but 0, a non-zero real number, then that number to the 0 power is always 1. That's a very important fact to remember. You could also put a number to the 0 power in your calculator, and it should also give you 1 if you forget. We have 2 more properties. So this is a power to a power now. Before I thought it was power to a power, but we were just distributing a power. Now we have a power to another power. So for any positive base b and non-zero real exponents m and n, or any non-zero base b and integer exponents m and n, easy, quick things to fill out. So here's your b value. We have m and n. If one is being raised to a power to another power, then that just means we're going to be doing multiplication between the two, right? It's kind of like you distribute it, but it's multiplying the powers together. So we get m times n in the exponent, b to the m times n. So we'll quickly try some. All right, so we have x to the 4th raised to the 5th power. So we'd multiply these two together and get x to the 20th power. Hopefully you remember this property from before. All right, in this case, we have 2 to the 3rd and 2 to the 6th power. So that would be 3 times 6, which would be 2 to the 18th power. And that would be a pretty big number, so I'm not going to continue solving that one. All right, and the last one here we have, not only do we have 5, but we also have z. So let's deal with the z squared. We would do 2 times 3 to get z to the 6th. And then we would do 3 goes to the 5 as a power, so it's 5 to the 3rd power. So that would be 125, 125 z to the 6th. There we go. Messing that up a little bit. And there's your answer. And I just simplified that one because it's not as big of a number. This number is pretty darn big. All right, one left. And this one you also should know. Negative exponent theorem. So for any positive base b again, and any real exponent n, or any non-zero base b and integer exponent n, then we have this property. If you remember, this property, b to the negative n, you can rewrite it without having a negative exponent. I'm going to show this to you in a very quick proof in this example, and then we'll reveal it. Example 8. So it says, prove the negative exponent theorem. First step is provided for you. So we're going to first suppose that we take b to the negative n, which is the same thing that's up here, right? I'm going to equal it to just some letter, x, some number. We don't know what it is. Okay, so I'm going to rewrite that down here in the next step here. So what I'm going to do is I'm going to multiply both sides of the equation by the same thing, something very special actually. I'm going to multiply both sides of the equation by b to the n. And same thing over here, b to the n. Remember, you can really do whatever you want to an equation as long as you do it to both sides of the equation. The only thing you really can't do is divide by 0. That's the only bad thing. Okay. So now we have b to the n on both sides, so that now looks even more confusing. But it's not really more confusing because we can put these two together because they have the same base, since I chose a specific thing to multiply on both sides. So we can actually add these exponents together. So now we have b to the n plus a negative n. And it gives you, you keep the same base, remember? Over here we have the same thing, x times b to the n. They don't go together, no same base, don't add exponents, nothing like that. All right, then what do we have over here? This is b to the, what's n minus an n, or n plus a negative n? That's 0. Look at that. And we might say, okay, well, what's b to the 0? If you remember, back at this property back here, any number to the 0 power is 1. So using that b to the n on both sides was useful because now this is just the number 1 equals x times b to the n. And lastly, I'm going to solve this equation for x and get it by itself. Since I have multiplication between the two, I'm going to move the b to the n on the other side by dividing by b to the n. So in this particular case, it is pretty important that b is not 0, right? That would be bad. You can't divide by 0. But up here, it does say a non-zero base. Or in this case, you have to have a positive base if you have a real exponent n. But in either case, you're not going to be using 0. So that's good. So we're dividing that. These would cancel out. We would get x by itself. I'm going to put it over here. We would have x equals 1 over b to the n. Now, who really cares? I mean, what did we even figure it out? What we figured out is if we have this as a statement that's true by doing our proof here, well, what was x originally? You see x originally was this. X is also equal to b to the negative n. So that must mean that 1 over b to the n is the same thing as b to the negative n. So this is a proof that shows b to the negative n is the same thing as 1 over b to the n. And we've done that, I think we did it before with subtraction, like we did like, I could just use b's anyway. B squared over b to the fourth, right? We used a property where we subtracted them, like 2 minus 4 is b to the negative 2. And then we said, oh yeah, well that's just 1 over b squared. Another way to do that is to write them out. You could say b times b is b squared. B times b, times b times b times b is b to the fourth. And you say, okay, well I'll just cross them out. 1, 1, 1, 1. There's 2 left on the bottom, nothing left on top, so it'd be 1 over b squared. So you end up getting the same thing, just using this properties a little faster. Obviously, would not want to write them all out every time. Our last example, then we're done. And you have some huddles. Yeah. Simplify the following expressions. Okay, so 2 to the negative 5 means it's actually 1 over 2 to the 5th. And I'll keep going with this one. 1 over 2 to the 5th would be 2, 4, 8, 16, 32. So it's a tiny fraction, 1 over 32. B, x to the negative 7 is the same thing as 1 over x to the positive 7. That's done. C, let's subtract these exponents. You get 5 minus 8. So 4 to the negative 3 power. But we have to keep going. Can't have negative exponents. As you well know from before, this is 1 over 4 to the positive 3rd power. And I'll keep going. 4 to the 3rd is 64. So it's 1 over 64. All right, that is the full lesson. I tried to go through it fairly quickly, but also enough to explain everything in case you've forgotten most of these power properties. And I think that's everything that we've covered before, except maybe b to the 0 equals 1. That might be the only new one. So go ahead and finish the huddle. There's 9 problems there. It says 1 to 9, but looks like there's only 8. Oh, here's the 9th one. Okay, and that's the rest of the whole entire thing. So the rest of it is just all huddle to finish that and turn it in.